Hi, in this short video, we'll dig a little deeper into RDBMS. RDBMS stands for Relational Database Management System. RDBMS has been there since 1969 when Edgar Cord of IBM Research proposed this way of storing the data. And for several decades after that, RDBMS has been the de facto standard for storing and retrieving data. Today, there are many RDBMS-based products like Oracle, IBM DB2, Microsoft SQL Server, which are all commercial solutions. And there are also many open source solutions, among which MySQL is very popular. In a traditional RDBMS, it spawns a separate process on the host system, and thereby it forms its own database tier in a multi-tier architectural solution. So since it is a separate process, someone has to start and stop the process, and it's in fact a very complex system which typically needs a DBA, database administrator, to maintain all aspects of the database system. So what exactly is a multi-tier application? Well, here is an example of a three-tier architecture typically used by e-commerce websites like Amazon, for example. This three-tier architecture consists of a presentation tier, a web tier, and a database tier. So in the presentation tier, it consists of all the client computers and clients' mobile devices, for example, through which the clients are connecting to the application servers. And the application server, typically which is hosted in some kind of a data center or cloud, will be the one which is hosting the web application, which is ready to receive connections from these various different clients. So that application, the web application, which is deployed on one of these servers, makes up the middle tier, which is also called as the middle tier or the web tier or application tier. They all pretty much mean the same. Of course, in many of the solutions, there could be multiple tiers in this middle tier itself. But for simplicity, we will call this entire set of applications that are running on the application servers, we'll call that as the web tier or the application tier. And finally, we have the database tier, which is the last tier of this multi-tier architecture in which the actual data is stored and retrieved. So whenever the client, for example, wants to store a specific data, then client typically first connects with the application server, and the application server in turn connects to the database server and then stores the data, retrieves the data, modifies the data. All those things are taken care of by the application server based on whatever the request that it is receiving from the clients. So in a multi-tier application, which is of this sort, this is a separate application and this is a separate application as well. So this application typically establishes a connection with this application and then communicates with whatever information has to be received and sent. So with the advent of mobile devices came the need for storing relational data on the client devices itself. However, mobile devices had limited computing power and memory, thereby being unfit to host a traditional RDBMS. Then came the need for lightweight RDBMS like SQLite and Apache Derby. So these embedded databases do not spawn its own process, and they are lightweight and they work just like a library program within the main application process. So there was no need to start and stop the processes like the traditional RDBMS. So now the question is, why is it called relational? So let's understand a few things in detail here. First of all, data is represented in a table. Data is arranged in rows and columns of a table. Table is also called an entity, and a row is also called a record, and a column is also called a field. The next thing is relationship. Once you have multiple tables which are created, you want to establish some kind of a relationship between them so that it helps you store the data more concisely and efficiently. The whole purpose of building a relationship is to ensure that there is no data redundancy and there are integrity constraints that are applied, and the data is stored in the most optimal fashion. And the technique of identifying and building relationships for optimal data storage and enforcing data integrity is called normalization. And the way the relationships are built between two tables is through primary key and foreign key association. So, primary key in one table is tied to a foreign key in another table, thereby establishing an integrity constraint between the two tables. So when you apply the techniques of normalization, your first goal is to bring it to the first normal form. A table is in first normal form if every cell contains a single value and not a list of values. First normal form also prohibits repeating group of columns, such as having several columns like item 1 column, item 2 column, and so on. So once you bring your database, which is satisfying the first normal form, you're now ready to take it to the next level, which is the second normal form. And a table is in second normal form if it is in first normal form and every non-key column is fully dependent on the primary key. If the primary key is made up of several columns, every non-key column shall depend on the entire set and not part of it. So once you bring your database to the second normal form, then you are ready to take it to the next level, which is the third normal form. And a table is in third normal form if it is in second normal form and the non-key columns are independent of each other and are also dependent on the primary key and nothing else. So once your database complies to the third normal form, you can also take it to the next level. However, that is beyond the scope of this discussion. When the database is satisfying the third normal form, which is the most popular one, your data is actually stored quite efficiently and redundancies are quite reduced and integrity constraints are applied appropriately so that the data is efficiently stored. Now let us look into this ERD diagram, which is in its third normal form. ERD stands for Entity Relationship Diagram. So to begin with, we have the customers table, and then we have the address table, login details, orders, order details, and products. So these are the tables that are created based on the various different types of data that are collected in a typical e-commerce website. And amongst them, there is a one-to-many relationship between the customers and address. Why is that? Because typically, customers have one or more addresses associated with them. For example, a shipping address and a billing address. And then there is a one-to-one relationship built between the customers and the login details table. Why is this one-to-one? Well, for every customer, we have one and only one password associated with the customer for logging into this website. And why is this not part of this table itself? Well, the reason it is pulled out as a separate table is because password is a sensitive data. and you don't want to associate an encrypted sensitive data with the rest of the data which does not need to be encrypted. And then we have one-to-many relationship between customers and orders. And why is that? Because every customer can be placing more than one order on this e-commerce website. So, and the orders in turn also has one-to-many relationship with the order details, because every order will have multiple products that would have been purchased against that order, and those product details are entered here in the order details table. And the products table also has a one-to-many relationship with the order details, because every order details could be having many products which could have been placed with the same order. And when it comes to a relationship between orders and products, it's a many-to-many relationship, because a particular order could have more than one products associated with that, and every product may be associated with more than one order. So there is a many-to-many relationship between these two. And of course, there is no direct many-to-many relationship that can be represented. It has to be through this one-to-many relationship with a join table. So this turns out to be the join table, which has one-to-many relationship between this and one-to-many relationship between products and order details table. Now comes the ACID properties. Now let's understand the ACID properties, which are the iron-clad guarantee of every RDBMS transaction. So what are these ACID properties? A stands for atomicity, which is all or nothing rule. C stands for consistency, which is also correctness of the database. I stands for isolation, which is the ability for parallel operations to execute without interfering each other. And D is durability. So that is, once a transaction is finished, the data is persisted for later use and does not get corrupted. And let's understand all of these properties with an example. So to understand ACID properties of RDBMS, let us take this very simplistic example of a bank database which has an accounts table. So this accounts table has just three columns: account ID, customer ID, and the amount that is available against every account. So here what you see is customer ID 1 has an account ID with the number 1, has $500 balance in his account, and customer ID 2 with account ID 2 is having $1,500 in his account as balance. Now let's assume that customer ID 1 wants to transfer $200 into customer ID 2. So if you look at the account ID is 1 for customer ID 1 and the account ID is 2 for customer ID 2. Let's for now, for this simplistic example, assume that the customers, each of these customers could have more than one accounts, and customer ID 1 is basically transferring $200 from account ID 1 that he's having into account ID 2 of this customer ID. Okay, so in other words, we are subtracting 200 here and crediting 200 to this account. And how will we do that? On the database side, let's take a look. So of course we need to have a where clause. Where account ID is 1, subtract $200 from the existing amount and then set that as the new amount in the bank accounts table. So this is an update statement, a simple update statement, where we are first subtracting 200 from account ID 1, and then that same 200 is credited into account ID 2. But let's, for argument's sake, assume that after this statement is executed, something terribly went wrong in the data center. There was some kind of a power outage that happened, and this statement got executed, but this did not get executed. So since this is a transaction, every simple statement is inside a transaction. So this executed correctly, but this did not execute. So what happens in the database now? Well, 200 got debited here in this account, but it did not get credited here on this account when the database crashed. So when the database comes back up, it is still showing the same thing. This is now 300 and this is now 1500. So in other words, we actually lost $200 because while transaction something terrible happened and $200 was lost into thin air. Obviously, that is not a consistent database. The consistency of the database is violated. And obviously, we don't want something like that to happen. So what do? Well, since this is an independent transaction and this is also an independent transaction, we landed up having this issue. Instead, if we made both of them part of the same transaction, then either the entire set of statements would have gotten executed or none of them would have gotten executed as per ACID rules. So how do we do that now? Well, you add this statement, which is start transaction, and then put these two update statements in between the start transaction and the commit transaction. This will guarantee that either all of these statements will get executed as one single unit or it will get rolled back if something went wrong. So after this statement is executed, if there is a power outage and something terrible happened, then it doesn't matter really. Even though there was a debit of 200 on this account, it gets rolled back because commit did not get executed. The database will ensure that since the commit did not get executed, the entire transaction is rolled back to its previous state. So now let's take a look at this ACID properties again. So atomicity. The entire transaction happens at once as one unit of work or does not happen at all. So it supports two operations: commit if all went well, abort if all did not go well. Consistency. The database must be consistent before and after every transaction. So in our case, it will ensure that the $200 is moved from one account to another. Neither it is lost in thin air, nor it is going to be pulled from thin air. Next comes the isolation. Multiple transactions can occur simultaneously without interfering each other. So again, in a bank, you potentially will have many customers making transactions and they all can parallelly do and they won't be interfering each other. Transactions will not be stepping on each other and they'll all be isolated from one another. Durability. Upon successful commit operation, updates to the database are permanent and does not get erased or corrupted due to any type of system failures. So this iron-clad guarantee is there with every RDBMS, whether it is Oracle, whether it is DB2 of IBM or Microsoft SQL Server or MySQL, it doesn't matter. All of them follow this ACID rules strictly.